Objects falling with air resistance, writing a differential equation. Now this video appears at this point in the sequence because although it's going to relate to mechanics, we are soon going to be writing and solving differential equations related to circuits. So we're going to get into the swing of things here by briefly diverting our attention back to mechanics. Here, we're going to analyze the motion of an object of mass m that is dropped from rest in a fluid. The fluid might be air, some other gas, or perhaps a liquid. Let us suppose that the fluid will exert a drag force on the moving mass that is directly proportional to the speed of the mass, according to this constant beta. All right, assuming standard SI units, what must be the unit on the constant beta? Well, if we look at this equation, we know that force is in newtons, and so there's the unit for beta right there, and speed is meters per second. So what unit must beta have in order for these units to cancel each other? It must have newtons in the numerator, meters in the denominator, and seconds in the numerator. You can see that the seconds would cancel, the meters would cancel. So the unit on beta would be Newton seconds per meter. And let's see, from Newton's second law, let me write that up there. Right, force is equal to mass times acceleration. Force is in newtons, mass is in kilograms, and acceleration is in meters per second squared. So a newton is a kilogram meter per second squared. So we could put that into here, and if we did, what would that yield us? That would say that we would have the kilogram would stay, the meter would cancel, and then we'd end up with a seconds in the denominator. So an equivalent unit would be kilograms per second. Either one of those would be fine. That's the unit for beta. Draw a free body diagram showing the forces acting as the mass falls. As this mass falls, it's going to have mg acting downward, and then there's going to be this drag force, which is equal to beta times the speed upward. At some point during the fall, the mass will achieve terminal speed v sub t. Write an expression for the terminal speed vt of the mass. By definition, terminal speed occurs when the mass is no longer accelerating. At that point, isn't it true that mg is numerically equal to beta times the speed? The terminal speed can be found by taking m times g divided by beta. Use the part A answer to show that our part C answer is dimensionally consistent. The speed, vt, is going to have the units meters per second. And the question is, do the units that we have on the right side match up with those? Mass is in kilograms. G, as we know, is in meters per second squared. Now, what did we decide about beta? Let me pull that sheet up here. Beta is either Newton seconds per meter or kilograms per second. Either one, those are the same. Let's use the kilograms per second one. If beta is kilograms per second and beta is in the denominator here, then I've got kilograms per second for beta. And what cancels? Kilograms cancels, second. Look at that. Good one. Looks good. Give ourselves a smiley face right there. So far, so good. In the two graphs shown, use a dashed line to sketch how the mass's acceleration and speed would vary with time if there were no drag force from the fluid. Let's do that first. If there's no drag force, then the speed, since it's dropped from rest, is going to be constantly increasing. Faster, 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 faster. And the acceleration will not change like that. Use a solid line to show how the acceleration and speed will vary with time when there is a drag force. The acceleration initially will start at the same value here, but once terminal speed is reached, then the acceleration is going to be 0. So I think the solid line should look something like that, where that value right there is the value of g, 9.81 meters per second squared. So if there's a drag force, the initial acceleration is the same, but at a certain time, the acceleration is going to drop finally to 0. And with The speed will eventually reach a point where it doesn't increase anymore. So it's going to approach a value like that, where this value right there is the terminal speed. So you can see the differences there if there is air resistance or drag compared to if there isn't. A differential equation is an equation having a variable and a derivative of that variable in it. That's what a differential equation is. Differential equation is an equation having a variable and a derivative of that variable in it. Last part. Via Newton's second law, we can write the differential equation that relates to our situation. Let's write that differential equation. All right, so Newton's second law is the net force is equal to the mass times the acceleration. Looking at our free body diagram, the net force on this mass will be mg minus beta v. The left side becomes mg minus beta v. And then m times a. All right, so how do we turn this into a differential equation? We do so by remembering that the acceleration is the time derivative of velocity. If we write this out again, mg minus beta v is equal to m times dv dt. There are several ways we could represent that differential equation, but that is a differential equation because it has a variable, namely in this case v, as well as a derivative of that variable right there, dv dt. We'll solve that equation in the next video.